Thank you. Yeah. So is this in row echelon form?
Yes, sir.
Yeah, the answer is yes, but let me go through that slowly. Okay, well, what is the question? The first non-zero, if there is a non-zero, if a row is non-zero, the first non-zero entry must be 1. Okay, so the last row is 0, so there is nothing to worry about it. The second row is non-zero, but the first non-zero entry is 1. Okay, so and that is in red. In the first row is non-zero, and the first non-zero entry is 1, so that is here in red. And so these are the pivots. Secondly, every entry above a pivot is 0. Well, above this pivot, there is no, that is in the first row, there is no question about an entry above it. But here is a pivot in the second row, and the entry above it is 0. Thirdly, the pivot on the I plus row is to the right of the one on the ith row. Well, so the the only such pivot that is relevant is this one, because there is no pivot in the third row, and this pivot is to the right of this pivot. So all these, all the conditions are satisfied. So this is indeed, so yes, this is in row echelon form. Okay, so now, so I want to look at the corresponding linear map A hat. So where does the corresponding linear map act do? It goes from some vector space to some vector space. So what are those vector spaces?
Space of column vectors.
Of what length?
So here it is for 3 cross 1.
Yeah, so it goes from column vectors of what length to column vectors of what length?
Five cross 1, 2, 3 cross 1.
Very good. It goes from column vectors of length 5 to column vectors of length 3. Right? Because what it does is it takes a column vector of length 5 and this is the matrix A. This is, so this is the vector V, this is the matrix V, A, and this is A, V, which I called V prime. So this is of length 3. Okay, so this is AV. So this is matrix multiplication. But this is also in notation A hat acting on the vector V. Okay, so there are two possible notations, A, V. Both of these are equal to the vector V prime. So this is, so let me, this is, so this matrix multiplication and this notation means linear map A hat acting on the vector V. In both cases, the result, this result of the operation is a vector V prime. So you can think of this in concrete terms as the matrix multiplication of the 3 cross 5 matrix with the 5 cross 1 matrix V to produce the 3 cross 1 matrix V prime. Or you can think of the linear map A hat acting on which eats the vector V and spits out the vector V prime. So as we saw from the discussion before the class began, it's really, really important to go back and forth between the two pictures. Okay, so now I can ask, what is the image? So when you have a matrix in row echelon form, it is, you can immediately read off the image. So the image of A hat of the linear map and the kernel of the A hat of the linear map are of interest. Whenever you are given a linear map, these two are of interest. And the point is that when a matrix is given in row echelon form, the image is immediately readable. You know, you can immediately read off the image. The kernel is slightly harder to describe, but still, with a little effort, you can see what the kernel is, and then you can actually determine the dimension of the image, dimension of the kernel, and you can check that the rank nullity theorem is satisfied quite easily for this. Okay, so let us ask, what is the image of the linear map A hat? So of course, since the linear map is given in terms of the matrix, one has to go back to the matrix and then think in terms of what the matrix does. Very good. So now let us go back to the matrix, which I will now, let me try and see if I can copy and paste. And as somebody pointed out, I should, if I press this enough, very good. Yeah, thank you. There it is. There is the matrix A. Okay, so now, as I have told you, what do the rows of the matrix, the columns of the matrix correspond to? Okay, so if I'm given the matrix like this, then actually, this is actually, you can really think of it as a something with only one row in which the elements are actually column vectors of length 3. So I claim that let me take the basis vectors for. So yeah, I claim that this is the columns of this are actually given by A hat E1, A hat E2. I should not put comma because there are no commas in matrices. A hat E5. Okay, in other words, where E1, E2, E5, the people are the standard basis for M51. So in other words, so first of all, is the statement clear? So this is, let me make this claim clearly and ask, is the statement of the claim clear?
Sir, these E1, E2, E5 are 3 by 1 vectors. 3 by 1
These are,
column.
E1, E2, E5 are the standard basis for M51. Together, these form the standard basis for M51. So they are vectors of length 5. So let me just write them down. 1 0 0 0 0 0 1 0 up to 0 0 0 0 1. This is E1, this is E2, and this is E5. So Shakti, so your question is answered.
Yes, sir. Yeah. Thank you, sir.
So as I said, this is a standard basis. So I should say is the standard basis. Okay, so you have A, you have the corresponding linear map A hat. When I hit E1 with A hat, I get a column vector of length 3, and the claim is that this guy is that column vector. And when I hit E2 with A hat, I get a column vector of length 3, and the claim is this is the column vector. And this is nothing to do with matrices in row echelon form. Supposing I'm given any matrix, this is the case. So in fact, if you look back at your notes, I have said that there is something called block multiplication of matrices. I have mentioned this in the notes, and this is an example of that. Neelabja.
Yes, sir.
Yeah, is my claim clear?
Yes, sir.
Just give me a second. Just 1 second. Okay. So my claim is clear. So then, how many of you actually already knew this? This is a very simple statement. And as I said, it is there in the notes. Okay, now that I have pointed this out to you, is this clear?
Yes, sir.
Okay. Shakti, is this clear now? I mean, I'm
Yes,
not.
sir.
Yeah.
Yeah.
Yeah. Okay. So once I have said this, can somebody tell? So I'm assuming that you agree with the claim. I'm not going to justify it. This is something that you can just verify by matrix multiplication. Okay. So once you understand this fact, can somebody tell me what is the image of A hat?
Sir, I think it would be the span of E1 and E2. Oh, sorry,
Yeah.
in three cross one. As
Yeah.
in
So
yeah.
let's call them E1 prime and E2 prime. Yeah. Yeah. So this is the correct answer. So let me write it down and then let's justify this. Okay. Image of the linear map A hat is the, so this is how it was said, span of E1 prime and E2 prime in 3 cross 1 matrices. So in other words, what is E1 prime? 1, 0, 0, and E2 prime is 0, 1, 0. So what will be the span of these? So can somebody describe for me explicitly the span?
The non-zero entry in first and two may be allowed. I mean, only 0 in the last row.
Exactly. So yeah. So this is of the form V1 prime, V2 prime, 0, where V1 prime and V2 prime are real numbers, arbitrary real numbers, right? Because the span is by definition arbitrary linear combinations of this kind. I'm sorry to be denoting this V1 prime, V2 prime, but this is the convention in the notes. The convention in the notes, which I try to be consistent, is that a vector has this arrow on top and its components are V1, V2, whatever is the length of the vector. Okay. So the guessed answer, we have not quite justified this, but this is the guess, and it's a good guess. So image. So this is a guess at the moment. Well, so let us prove this. Let us justify the guess. Okay. So let us. So in fact, I think there is a word that mathematicians use for a guess. It's conjecture. Okay. So let me call this a conjecture, which is because it's a good guess. Okay. So the claim is that this is this is the span. So the question, does image contain, because the span must certainly contain these two vectors. So does it contain E1 prime and E2 prime? What do you think?
Yes, sir. They are like in the column vectors itself, like of the matrix A. So they have to be.
So say it somewhat more
right.
more precisely.
Right. E2 is mapped to E1 prime and E4 is mapped to E2 prime, and so.
Very good. So A hat of E2 is E1 prime, and A hat of E4 is E2 prime. Okay, so is this clear to everyone? Because that follows from this this claim. See, so A hat E2 is the second column here, and that is E1 by definition of E1 prime. Siddhant, you look puzzled. Are you okay with this?
Yes, sir.
Yeah. Okay. No. It's good to see people's faces, because then I can kind of, first of all, I know I'm actually talking to not a dog. Yeah. Okay. Great. So now the question is this it? So can we now conclude? So certainly, since the image is a linear subspace, if it contains two vectors, it contains their span. So we know. So we can conclude. Image A hat contains span of E1 prime and E2 prime. Now the question is it equal? An equality. So look back. Yeah.
Hello, sir.
Hello. Yes. Who is this?
Sir, I'm Nilabjo. Sir, when we see that the image contains E1 hat and E2 hat, then
E2 prime, E1 prime and E2 prime. Yes.
Yes, sir. And so as the image is a subspace, that's why we claim that the span of it will also be contained, right?
Exactly.
And,
exactly.
Now
the
we
question
check. Okay.
Yeah.
Okay.
But now the question is whether the span, the image can be bigger than this.
So I don't think it can be.
Yeah. That is.
So we just
that's
need to see if it contains any new basis. I mean, apart from this, any new basis of the space or not.
You be a bit more specific, no, because we are not talking about basis. So
Sorry, sir.
So no, just you have the right idea, but just say it precisely. Just take a minute, take 2 minutes, take 3 minutes if you must. You have the right idea, but just say it properly. So let me just frame it for you. Everything is contained. These are all subspaces of 3x1 matrices. Okay, this is one subspace. This is another subspace. This subspace is contained, and the question is this an equality or not? So now you said something. I think if you make it more precise.
Sir, could I try?
No. Who just spoke? I want to give him some time to think. Who
Sir,
just spoke?
I am Nilabjo, sir.
Neelam, okay. Do you want to take another 1 minute to make your question idea precise?
Sir, I was just saying that if E3 prime, I mean the vector E3
Yes,
prime
yes,
is there
okay,
in the
okay,
column
okay.
or not.
If E3 prime is in the image or not?
Yes, sir.
Yeah, okay.
If that's not there, then we have exhausted the image.
So no. Why? So supposing it was a supposing if it was a I mean, why that specific vector?
So because E1 and E2 are all E1 prime and E2 prime are already there,
Right.
and so all their linear combinations are there, and
Right.
now if
so you're saying now if this is
So we can
not
show
a,
that it could not be greater than 2. Either greater
the
than 2 or
point
less.
is, okay, let me now see let me just say, if this is not an inequality, then this would be forced to be an equality, right? Because this is dimension 3, this is dimension 2, so this is a subspace which is sandwiched between this and this. So if this is not an equality, then this would have to be equal to this, because the dimension of this must be an integer which is either 2 or 3. If it's not 2, it must be 3. So which means this is a subspace of this with the same dimension. So this would be an equality, in which case this must contain E3 prime.
So does this essentially trickle down to the trichotomy of real numbers?
Oh my
I mean,
gosh. What are
yeah.
the real numbers?
I mean, the dimension of this cannot be greater than 2 or less than 2, so it has to be equal to 2.
This is not to do with real numbers, it's to do with integers.
Yeah, I mean natural numbers also.
No, natural numbers. Yeah, I mean, okay, if there is no...
We are essentially doing the same thing, contradicting.
Don't say essentially, because we are doing something with vector spaces, and it is not. I mean, it is not essentially. Certainly, it is a fact that there is no integer strictly between 2 and 3. But that is not I mean, that's just incidental. So, what one is saying is that if I have a subspace of a 3-dimensional vector space sandwiched between a 2-dimensional subspace and the whole space, then it has to be either the whole space or the 2-dimensional subspace. There is linear algebra going on here.
Yes, sir. Yes, sir. Sorry,
Yeah,
sir. Sorry.
so, and if you say essentially, you're somehow missing the point. That is
Yeah.
Okay. So having gotten that out of the way, so Nilabja, you're absolutely right. So to show that this is an equality, it is enough to show that E3 prime is not in the image. So this is an equality. And to see this, it is enough to check that E3 prime, which I recall for you, is this vector, is not in the image. But that's true, but you can in fact just look at what A hat does. So now you don't need anything. You take a matrix of this kind and let it act on any damn vector of length 5. Okay. What will this entry be? This entry is got by, so sorry, this is
3 by 3.
3 by 3. Okay.
Sir, could you just repeat the question once?
So see, the question is, so we know that the image of A hat contains the span of these two. Okay. We want to show that it is on the nose, just that span. Okay. So now my point is, now take any 3 by 5 matrix with the last row 0. Let it multiply any column vector of length 5. What will this red? What will happen here?
It will be 0.
Because this is got by multiplying this with, let me follow the red dot. This is got by multiplying this with this, this with this, this with this, this with this, and this with this, and adding up the results. Right? That is how matrix multiplication works. When I multiply whatever this is, when I multiply by 0, I get 0. Whatever this is, when I multiply by 0, this I get 0. So all these guys are 0. So when I add them up, so I'm always going to get 0 in the last position. So the image, so in other words, quite independently of all the previous discussion, we can check that the image contains E1 prime, E2 prime, and is contained in blah, 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 0, V1 prime, V2 prime, V1 prime, V2 prime in R. Do you get what I mean? See, that previous discussion was, I wanted to pursue that because there was an intuition there that's important. But we don't need that discussion, because let me repeat. I'm going to just do this somewhat more neatly. Okay. So come here. Just look at this. Okay, we have reached here. Now I want to claim this is an equality. Okay, so I'm going to, so this argument was indeed correct, and in fact we can go that way, but I am going to say, now I'm going to say the following. Even, damn, these colors are, the span of E1 prime, E2 prime is contained in the image of a hat. And I want to claim that in fact the image of a hat is contained in, so this, by the way, is V1 prime, V2 prime, 0, V1 prime, V2 prime, real numbers that we've just saw. The span of this is this. But I claim that this is also contained here in the same thing. And why is that? And that is where the big, so why? Because if multiplies any 5 vector of length 5, the resulting vector, 3 vector, by that I mean a vector of length 3 must have the last entry 0. So that was just what I said earlier. Blah 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 0 0 0 0 0, and take any damn thing 1 2 3 4 5. The resulting vector will have this entry 0. Okay, so this was a quite a long but necessary this thing. Is everybody with me? Has everybody stayed with me during this long discussion? Can I go on? Yeah, Swaminathan, you're nodding your head. Yeah.
So can I ask a question?
Yeah, sure.
Here, you had the row echelon.
So who is
this
this?
is Roman. So can you hear me properly? Or is my
Yeah.
So you started with the row echelon form.
Right.
And then you said that the matrix which you multiply by will also have no zeros in the bottom row. I'm not sure where that comes from.
No. So this, sorry, what did I say?
Blah 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 matrix, the one that you said pre-multiplies. That one has zeros in the bottom.
I'm still trying to see what does a hat do. Okay, can a hat acting on a column vector of length 5 somehow magically produce a vector with a non-zero third component?
Oh, okay. So that's still the row echelon form.
Yeah, so
received
I'm saying it's not, you don't need to use the fact that A hat is in row echelon form. All you need to use is the fact that the last row vanishes. That's why I said blah, 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 blah for the first two rows.
Okay, sir, thank you.
Okay. So see, my point is, let me do this slowly. Come, are you with me till here? Everybody? At least till here. Right? We got till here. Is everybody okay with this? That the image of A hat contains E1 prime, E2 prime, and therefore it contains their span, and the span is precisely this. So is everybody on board with what is in the red outline? Amit, right? Who asked? Romit.
No, sir, Romit, yes.
Romit, yeah. Do you agree with me? This everything
Yes,
in
it's
the
fine.
red outline you're okay with?
Yes, it's fine. Thank you.
Yeah. So now I put the same guy here, and then I claim that this is actually included here. Then I would have equality of this and this, because this is exactly the same as this, what I put here. So if I prove this inclusion, all this must be equal to this, must be equal to this. Romit?
Yes, sir.
No, I don't want you to agree with me because I intimidate you into agreement. So you have to. So first of all, let's go slowly. We want to determine the image of A hat. We cleverly see that it contains A1 prime and E2 prime, because this is the second row, second column. This is the fourth column. Therefore, it contains their span. And the span, if by inspection, is this. Precisely consists of column vectors of length 3 whose last entry is 0. Romit, do you agree with that?
No, sir, it's fine. I got it. I mean,
Yeah. Okay. No, because now that I've started, I will go through this thing. Now I want to prove that this is an equality. To prove that, I take this guy and put it here, and then I prove this equality. So once this contains this and is contained in it, then must be equal. Okay. So now I have to show that the image of A hat must be contained in the set of vectors with the last entry 0. But A hat is a matrix of this kind where the last entry is 0. I mean, I don't need that it's a row echelon matrix, etc. All I need is that the last row, sorry, I keep saying last entry, last row is 0. So now take any such matrix and hit any column vector of length 5 with this matrix, and see what happens when I multiply out. That this entry is got by this matrix multiplication of this row with this column, and that gives you 0. And that proves this equality, which proves that these three are equal. Okay. So now,
maybe I'll email you about this later.
Sorry?
So maybe I'll email you about this later because it's slightly.
You still not clear, Romit?
Yes, I mean, it's back to the same thing because at the end you said you're matrix multiplying it.
Yes.
But if you have a row echelon form, then we don't matrix multiply it, right? So
Okay,
saying,
just give me a minute. I'll get back to you. Okay. Anyway, I need a break, and we will resume this. Of kernel. So now, so I have just enough time to discuss the following important question, which is independent of this. Suppose A is a n cross n. Now, matrix. let me say M cross N. So it's a square matrix in row echelon form. And A is invertible. That means A inverse exists. So don't immediately think determinants, formula for inverse, etc. Just that it is invertible. That means there's an inverse. Okay. Then what can you say about A? So given today's experience and the definition of row echelon, you should be able to at least conjecture the answer. And in fact, I may have even said the answer in an earlier class. But just think in terms of what we learned today and what you know about row echelon matrices. Yeah. So already there is a guess in the chat, but so let's first of all put down the matrix, at least put down the box. Very good. Romit has the right idea. So so this is A, and so the correct starting point is to ask, can this happen? Can the last row be 0?
No, sir, because I think the map needs to be surjective actually.
Yeah. If the last row is 0, then as we just saw, then if you hit any vector of length n with this matrix on the left, then the resulting vector of length n will have the last entry 0. So the map A hat will not be surjective. So this is not possible. So the last row will not be, cannot be 0. So the row echelon thing means that this will go till here and there'll be a pivot 1 and then something like this. Okay. Now, can there be something here? Is this possible?
So right now there can't, like, we can say there can be stuff, but then like we'll come to the conclusion that for that condition where the I plus 1th row has to be to the right of the ith row, and we have
no. You're mixing up your terminology. Say, just listen to what you just said. You said what you I'll just quote to you what you exactly said. You said the I plus 1th row must be to the right of the ith row.
The pivot in the I plus 1th row has to be to the right of the pivot in the ith row.
Yeah. So when you talk or write math, it's really important to listen to oneself. I'm not saying this to chastise you. These are habits because when in normal conversation we speak and we assume that there is a kind of autocorrect that people apply when they are listening. But in math, it's really important you be precise. Yeah. So your point is taken that because pivots in each successive row must be strictly to the right. So the only way that can happen is that the pivots are going to be the last pivot, the last row, the pivot must be right here in this corner. And then you will go, so just keep going up, and then the pivots must all occur along the diagonal. And because of the rule that the entries above a pivot must be 0, you will get 0 here, and we already have 0 here. So A must be the identity matrix. Finito. So this is the level of okay. So I don't expect you to sort of give a sort of legally correct proof of this fact, but you should at least think about this and convince yourself that this is the case. So because otherwise it's enough for your course, for our course, for you to know this fact and have a kind of some idea of why this is true. But the basic fact is that the only matrix, invertible matrix in row echelon form is the identity matrix. Now, yeah.
Like, are we like not considering the zero matrix? Like all elements are zero?
I said the only invertible matrix in row echelon form is the identity matrix.
Okay.
Yeah. So the conclusion, so if A is in row echelon form and invertible, A is M cross N and in row echelon form, A is the identity matrix. So now recall what we said, recall any M cross N matrix given any M cross N matrix, you can find elementary M cross N matrices EK, E1 such that E1, EK, E1, E2, blah, 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 EK acting on A is, which I call A prime, is in row echelon form. So this is a general statement. So M not necessarily N. Now specialize. 1 minute. I'm supposed to call him that in a minute. Specialize to M equal to N, and suppose A is invertible. So then what do you say? We have their axis E1, EK such that EK E1A is A prime. Now this is row echelon M equal to N. So this M cross M. M cross M. And since A is invertible and elementary matrices are invertible, this is invertible. So A prime is identity. So A EK minus 1 E1A is identity. which implies A is ek minus 1, ek minus 1 up to even minus 1. So these are all elementary matrices. Implies any invertible matrix is a product of elementary matrices.
Excuse me, so
Yeah.
do we have the formal proof of that of this assertion that every matrix could be reduced to row echelon form?
No. The proof is there in Artin, but I don't expect you to know this.
Okay, understood.
And I'm not even putting it in the notes. Yeah.
Yes,
Okay.
sir.
So, yeah. So I think that is